Hello everybody. Okay, in this video I want to talk to everybody about the concept of the atomic mass and how to determine it. Okay. The atomic mass is an important part of every element in the periodic table, and so we've got the periodic table right here. And notice all these numbers along the bottom of the periodic table. These are the atomic masses. And I'm assuming everybody knows what the number on the top here, this is called the atomic number, the number of protons in the nucleus and the number of electrons around it. But it's very easy to get confused between mass number and atomic mass. Now I'm going to zoom in on chlorine here so we can see this a little bit better. So take a look at the chlorine here. The chlorine has a atomic number of 17. So 17 protons in its nucleus, 17 electrons around it. It has an atomic mass of 35.4527 or 35.45, however you want to shorten it, atomic mass units, or AMU. This number down here is not the same as the mass number. That's very important to understand. Not the same as the mass number. Okay, what we're going to do today in this video is to figure out where this mass comes from, because notice it's not a round number at all, whereas this one is. Remember that the atomic number is the number of protons in the nucleus equal to the electrons around it. The mass number is simply the number of protons and neutrons in the nucleus, so it's got to be a whole number. Okay, this cannot be the mass number because it's not a whole number by any means. So we've got to figure out where this comes from, and that's what we will do. So we said the atomic mass of chlorine was 35.45. Let's just round it to that. The atomic mass of chlorine. Alright, so the goal today is to figure out where this comes from, where this 35.45 comes from. Now, the only way we're going to be able to figure this out is if we know something about the different isotopes of chlorine that actually exist naturally. Now, for those of you that don't know what isotopes are, isotopes other than the Springfield baseball team on The Simpsons is actually two isotopes are atoms of the same element that have same number of protons, but different numbers of neutrons in the nucleus. All right. And it turns out every element that has isotopes exists as a certain set number, and it just is the way it is. Chlorine, for example, exists as 2 isotopes. Okay, it's not 3, not 10, it just happens to be 2. That's just the way they naturally occur. There is one isotope of chlorine known as chlorine 35. There is the other isotope of chlorine that is known as chlorine 37. These numbers are the mass numbers of each of those isotopes. So isotope 1 has a mass number of 35. Isotope 2 has a mass number of 37. Okay. Now, as we said on the periodic table here, every atom of chlorine always has 17 protons, regardless of whatever else is going on. So for this chlorine 35, then, it's got 17 protons, and in this case 18 neutrons in the nucleus. Chlorine 37 has 17 protons and 20 neutrons. So that is the difference between the two, the number of neutrons inside the nucleus. This one is slightly bigger. Alright, it's got a slightly larger mass because of the larger number of neutrons. And there's one other fact about these isotopes that we have to know as well. And that is that they don't necessarily exist in equal amounts. Okay? It turns out that chlorine 35 exists in a much larger amount. It exists in about 75.8% abundance. And the rest a smaller amount is 24.23% of the chlorine-37. So you can see this is approximately 75-25, approximately 3 to 1. So the idea is there is more chlorine-35 naturally existing than chlorine-37. What that means is when you take the weighted average of these, and we'll talk about that in a minute, the weighted average comes out to be closer to 35 than 37 because there's a larger amount of the chlorine-35. Alright, so let me show you just exactly how we do this. To get to the atomic mass, I'm just going to use AM for atomic mass here. We are going to take the sum of everything that we have here, and by sum I essentially mean the weighted average here. So we're going to take the mass of our chlorine-35, which I'm just going to round to 35 AMU. It's actually 34.97, but we're just going to say 35 just for the sake of simplicity here. We're going to say the mass of the 35 AMU isotope multiplied by its percent abundance. Right? Now remember, the percent is always something over 100. So 75.77 divided by 100 gives us 0.7577. That's for our chlorine-35. Then we're going to do the same for our chlorine-37. And we're going to multiply that by its percentage abundance divided by 100. And that's for our chlorine-37. And so what we end up with is that this times this plus this times this gives us the atomic mass of chlorine. Remember what I said, the atomic mass is the weighted average of all the isotopes, and you may have an element that exists as 3 isotopes, or 4 or 5. Okay, and so all you do is this is just isotope number 1, this is isotope number 2, and you just keep on going until you've figured out the weighted average of all the isotopes, and just add them all up together, get the average, the weighted average, and that gives you your answer. Okay. And essentially that is how we figure out the atomic mass of any element. Alright, if we just do one quick example. Copper exists as essentially 2 isotopes, copper-63 and copper-65. Alright, the copper-63 has an abundance of 69.17%. The copper-65 has an abundance of 30.83%. Okay, calculate the atomic mass of copper. Alright, well, we're just going to do exactly the same thing again. To get the atomic mass, we are going to take the mass of our isotope number 1, multiply it by its percentage over 100, add that to the mass of our second isotope multiplied by its percentage over 100, that should be 0.3083, sorry about that. And what we get as an answer is 63.55 AMU, atomic mass units. Now let's go back to our periodic table. Let me zoom back out and let's see if we can find, where's copper? There it is. Remember what we said for the atomic mass of copper, 63.55? 63.546, just shown to a different number of significant figures. If we round this up to 4, it becomes 63.55. So we know that what we said is true. This is the way to determine atomic mass of any element that exists as a set of isotopes, and that's it. Alright, thank you.